Okay, so are we still waiting for stragglers or? Okay, yes. On cue. Are we waiting for stragglers or?
We're not waiting.
Say? Okay. I'll try. Okay.
John, do you have control of the lights?
Oh, I probably had lunch in. No. Kind of. Okay, I'm told Chubby was being held hostage. That's awful. How dare you? Anyway, so I'm going to start off with the problem, because that's what we do here. So some of you have occasionally written like Excel formulas or programming things where you have a lot of brackets, right? And maybe you get something that ends up like, if I only got one color? Oh well, oh no, I've got more colors. Yeah, you might get something like this where the brackets are quite deep, right? Okay, so you're all familiar with this kind of thing, and occasionally the computer will, occasionally you'll try and write something like this. And you'll get an error message for an extra bracket or something, right?
Can you put on
The light?
It's on
the board lights.
for the that shines onto.
John,
I
on
think
the
you put
table.
it on the.
On the table.
There's a switch just behind the camera thing somewhere on the side. I think further to the side.
Thank you very much.
Okay, much better.
Nice thing about Excel is it fixes it for you, John.
That is the only nice thing about Excel. But you know that is a crime against, it's a tragedy. But anyway, it's possible that you do get this kind of thing which is valid, and there are kind of bracket permutations which are not valid. Okay, so one of the rules about valid bracket permutations is that every start has an end. So you have the same number of start and end brackets, right? Okay, now we get on to the interesting thing. How many valid in-pair bracketings? Because they count a lot of things. So Richard Stanley, whose book we were, looking at yesterday and a bit of today, one of his exercises says, here are 66 definitions of the Catalan numbers, or 66 things which are counted by the Catalan numbers, and you should prove that absolutely all of them are in fact counted by the Catalan numbers. Now 66 sounds like a lot, right? Yeah. And the joke is that you don't just prove that they're all equivalent to dichopods, you find a bijection between each of them. He then went on to publish like another 300 or something different extra things, which anyone who feels like can, go and prove all of those. I think that's a joke. Okay, and of course if you don't see this nice bijection, you can do the same proof we had last time, which is, look, this first bracket, either, it only goes down at the end, only gets closed at the end, and there are going to be, Bn is n minus 1 for if it starts and ends, plus, well, it could open and close at some point k, right? In which case there'd be k minus 1 in between, times by, okay, so that's the same Catalan recurrence.
Sum over OK.
Yes, thank you. Sum across k. Okay, and I think that's actually summing k is k is 1, 2, and minus 1, which we can just write, saying v0 is 1 as a sum of vi v n minus 1 minus k minus I cross I. Okay, so I'm going to spend a bunch of time today on different things that get counted by the Catalan numbers. So, what are the internal angles of a 7-sided polygon? What do they add up to?
900.
900 degrees, right? How do we prove that? Well, we draw some triangles. Right? We draw some triangles. We see that we have n minus 2 triangles and times by 180. Okay? So here's a question. How many triangulations are there? I mean, the way we chose these triangles doesn't really matter, right? We could equally well have 7 might not have been the best choice, but we did this, and we could equally well have done, something like that, right? That's also valid triangulation. There are also 5 triangles. Angles are the same, yeah. So, question. How many are there?
When you counting them, you're not taking into account the symmetries, are you?
No. So that's a good question.
Like in a square, does that count as 2 triangulations?
Also,
Like if you have a square, does that count as 2?
yeah, there are 2 ways to triangulate the square. There's the 1 through diagonal and the 2 4 diagonal. Okay, so let's actually do some. Let's try and work out some of these, right? Okay, the answer I'm sure has been hinted at quite a bit because I just said, hey guys, we're doing Catalan numbers.
I think I see how.
Very good. But let's just do a couple of them, partly because if I'm talking about all these Catalan number things, you should really, write out some of the numbers at some point. So when you see one of those sequences, you go, oh, Catalan. Okay, so how many ways are there to triangulate the triangle? Very good, 1. How many ways are there to triangulate the square? 2. 2. Very good. 2. How about pentagon? Sorry? Okay. An answer?
5.
5 is correct. So it's a little bit less obvious, so let's draw them out. Okay, so 1 we can put here. And 1 there. And if we insist on 1 and 2, then that's the other one. If we, and the other thing we can do is 1 and 4. Right? Can't put 1 there. But we can sort of pair it off there. And then there's that. No, there's not that. We've shown it. There's that. Okay, and the same. Probably just counting these. Okay, and all of these look like they're kind of pick a corner and draw things in. So the last corner is that. 5 ways to do that. How about the 6-sided one?
14.
Oh, yes, that is the answer. Okay, should we write out all of them? Yeah, please. They're like no. Okay, then 42 is the next one. Doesn't matter. Okay, so now, how is this a Cat-M recurrence? No, never put the top. Okay, so and for a straight line, 2-sided one, we have C0 is 1, C1 is 1, C2 is 2, C3 is 5, and so on. Okay, so, well, C0 is 1, C1, 0 times 0 is 1, C2 is C0 times C1, times C0, which is 1 times 1 plus 1 times 1 is 2, C3, which is then 2 plus 1 plus 2, which is 5. Okay, and this is the last one I'm going to actually write out. 3. Which is 5 times 1 plus 2 times 1 plus 1 times 2 plus 1 times 5, 14.
What is the notation of the C0, C1?
Yeah, the CI is the end.
Catalan number.
Yeah, the C1 is the first Catalan number, C4 is the fourth Catalan number, which is 14.
Is this what you're doing, the sum BI?
Yeah, so I used so the BIs are the CIs.
Yeah.
When we wrote that, we were sort of talking about them as bracket numbers. And after we paired them up with dipods, we realized, oh, these BIs are actually the same as our CIs. Okay, everyone good with that? Okay, cool. So we've checked this for 3. And you know what? I'll say we've checked it for the 4th one. So that's a proof, right? No, really. Okay, so how are we going to prove this? John, yes.
So, the way I think I see the way the recurrence comes in. So, you take a polygon.
Okay. Sure. We have inside the polygon.
Yeah.
Okay, maybe those things happen. Yes.
And once you've drawn the first line, it becomes 2 polygons with different, smaller, less size.
Yeah. So we'll connect number 1 up with number point K.
Yes.
Right?
And now you've got
Okay. So remember, this is an n+2 polygon, sided polygon, right?
Right.
So Cn. Well, how many are here? K minus 2, right? So I think we're going to maybe get a little bit of indexing off. That's okay. Yeah, it's the sum across K of the things on the side and the things on the side. So we should be careful. This is K minus 2. No, actually, it's K-sided. It's a K-sided gun, right? Because it's got points 1 and 2 as well. This other one is a, well, yes, M. K and C. Okay, and I'm going to skip over the indexing. Okay, yeah.
Where did it be C and minus K?
Well, there's C and minus K over here, and on this side there's K. Yeah.
Can't you always choose the closest point first?
Say?
Can't you always choose the closest point first?
Well, the closest point to what?
Well, your starting point. And then,
Yeah.
because you're going to have to.
Well, no. So in a triangulation, one is paired with a particular. Well, it could be paired with 2. That's right. So yeah, we choose the first one. And that's the trick I'm saying. So we choose the first one. So we know there's sort of nothing over here. And then, yeah, these things all are getting either minus 2 or. Yeah. John?
What about the case where there isn't a diagonal connecting to 1 on the triangulation? Like if 2 and n was connected, for example.
2 and n are connected. So do we... So I think I might just have messed up this proof. That's bad. Yeah, that can happen. Okay, so...
Wait, isn't it just the first, the bn minus 1 something? Like, yeah.
So? Okay, I have...
Maybe don't write a generic, maybe draw a polygon with a specific number of sides instead of displaying inside it.
Okay, yeah, so let's work on this together for a bit.
Wait, John, can you just add in the c n minus 1 to that sigma and then get that thing, which is the Catalan number?
Maybe, so let's see. So what's our approach here? So I've got some polygon. So how do you want to do this? Yeah, there's something in this proof, so it's okay. I've got a lot more sequences to come, which are Catalans. Okay, let's leave this on the board as hopefully a change. And we'll move on to the next encounter by the headlands. Okay, so permutations of the multiset. Have you guys seen multisets? Okay, so it's a set and some elements might be repeated. Okay? So the set which has 2 1s, 2 2s, and so on, and then finally 2 n's. How many permutations?
Permutation.
Yeah.
So there's 2n things in there.
Yeah, 2n.
Factorial over, there are n repetitions.
Yeah, in repetitions.
So it's
So that's, yeah, divided by 2 to the n.
2 to the n.
That one's not going to Okay, so here's another one. Sequences. 2, 3 dot dot less than equal to an, where ai is less than equal to I. Okay, how many sequences like that do we have? Should we do a few small cases?
Yes.
Okay. And I'm going to call these. Okay, so how many sequences of length 1 do we have like this? Just 1, right? And what letter do you want to use for the sequences? S's? Yeah, okay, so S1 is 1. How about for length 2 sequences? Say? 2. Yeah, and the sequences are 1, 1 and 1, 2, right? How about S3?
5.
Yes. What are they?
1,
1, 1, 1, 1, 1, 2, 1, 1, 3, 1, 2, 2, 1, 2, 3. They're 5. Okay? So now we're feeling Catalani again. How about S4? Yeah?
Wild guess.
Mm-hmm.
14.
14. Well, let's see. 1, 2, 3, 4. 1, 2, 3. 2. 4. 2, 3, 1, 2, 3, 4. Oh no, that's awful. 1, 1, 2, 2. 2, 3. 2, 4. 3. 1, 4. And yeah, is that 14? Yeah, 14. Okay, and naturally there are 42 and of length 5 and so on. So, how do you guys want to prove this?
So John,
Yes?
does that say 1 equals A1 or 1?
Yeah,
A1.
A1 is 1.
Oh, I see. Okay.
Yeah.
Yeah.
And all the AIs are bigger than 1, as I guess.
Always 1.
If you draw the sequence graphic, you get a type path.
Yeah, that's it.
Gotta trust me that I was thinking the same thing.
We believe you.
Then you go right or up.
Yeah, so there's 1, 1, 1, 1, 2, 2, 3, 3, dot, dot, in, n. And yeah, we start over here. The first one has to be 1. And somewhere below that, there's a 2. Maybe we then have 2, 3. And so on. And you just draw the sequence. And you get a like path of length n. That go too quick?
Yeah.
Okay.
How does that relate to the sequence that you've drawn?
Okay, so these points over here are points I, AI.
Yeah.
So, oh. Right, so let's maybe take a particular one. Let's take 1, 1, 2, 4. Okay, so the first point is 1, 1.
2, 1.
Yep. 2, 1 is over here.
3, 2.
3, 2 is about there.
And 4, 4. Okay.
And then 4 is here.
Yeah.
And we still have this diagonal. Okay, so we go there. So we go in. So what do I do?
Probably not to scale.
No, it's not. Okay, sorry. Let's be a little bit more rigorous with this. Okay, so that's our origin. Okay, start at 1, 1. And let's go, let's end at 3. So end at 3. That one's 2. And that's 2, 1. And each of these just becomes a little thing. And they bear off in flat points. I feel like that wasn't quite as clear as I wanted. And another little point. 2 inches n grows at roughly this rate. Okay. So calculate numbers. She's in grows at roughly 4 to the n root pi into the minus 3 over 2.
Is the number also in to n, 4 to the n, and
Divided by the square root of pi times n.
is it pi n?
Yeah.
Oh,
And so, yeah.
okay. Is it just some
Oh,
approximation
it is an approximation. So you
that someone
get it,
right?
yeah. So you get it from generating functions.
So is that useful for,
Sorry?
is that useful for, let's say, technology where space runs out when you're doing combinations? It's a
More or
It's a
less.
simpler calculation to go
Yeah. So you don't
to the
have.
end.
Well, so you don't have a calculator in Olympiads, so that becomes helpful.
Right.
Sometimes in research things, you find, oh, I've got this summation over these things, and I need a lower bound to show that this thing converges. And sometimes that's good enough. Okay, are there any questions?
How accurate is this approximation? Like if you round it, how close do you? Or is it not close enough?
It's pretty close. I think it might even be nearest integer. Well, let's do an example. Okay, so 8 choose 4 is 70, right? Okay, so this would be 4 to the 4 of the square root of, well, pi times 4.
Yeah.
Okay, 4 to the 4? 64.
5 to 2 to the 8.
5,
64.
2 to the, yeah, 5,
No, 256.
256 over 2 root pi. That's 128 over the square root of pi. Does anyone have a calculator? One time in an Olympiad camp that you'll ever be able to use a calculator?
1.8.
Okay, Fran?
1.8 ish. The root 5.
144.4.
Say?
Wait.
You're dividing by like 1.7.
72.216.
72.216.
Yes.
Yeah. Now, I don't know. So, if I remember right, let's do another one. 10 choose 5 is 252, right? Am I getting that? Okay, so that's what? That's, we claim that's 4 to the 5 of the square root of pi times 5. 1024 over root pi root 5. Correct?
258.368.
Okay, so it's not the nearest integer, but it's within a few. Cool. Okay. Did anyone think of a nice bijective proof for this one? Anyone? No?
Can't you? I mean,
Proof here?
I'm
Yeah?
simplistic. Sorry. I mean, can't you just say how many ways are there to choose the first point?
What do you mean by the first point?
Well, you've got. I'm sorry. Okay, so let's take a hexagon.
Say?
Take a hexagon.
Okay, cool.
And you're going to start at one point in your triangulation.
Okay.
You've got to start somewhere, and you can start at any of those 6 points.
Well, careful, because I mean,
You might get repetition.
This one might not be in a thing. Right? It could do that.
You can't. Why?
Well, I mean, there is a triangulation that doesn't have this one as an event with anything.
Okay.
So, not quite.
Yeah. Okay.
But that one's the first point then.
Sorry?
Is that what you're doing?
So okay, I'm thinking. I mean, you can't, but that is one of them. I mean, that is.
That is one of them, but you will get some repetition and you won't get all of them.
Yeah.
So,
Yeah.
Sean?
On the what you did,
Yeah?
if you just add the C n minus 1 and then you do the pairwise pairing of the others, then you get the Catalan numbers and that's
Okay, so this is point 1.
So in case you exclude it, it's
Okay, so possibly it's excluded,
then that's
but this is an n-1 polygon.
yeah.
Okay, so the number of ways, I'm just going to call these Pn because we don't know their catalans yet. So Pn, well, it's Pn minus 1 if we're in this world, right? If that happens.
And you just add all the other
And
pairs.
otherwise, we're something like that.
Yeah.
To k, and that's summing over k in the way you'd like. Cool, thank you. Okay. Okay, so k-name numbers are cool, but it turns out they don't count everything, which is weird, right? Because of the 360 sequences you think you've done, but I'm going to talk a little bit about a related sequence called Månskin numbers. Månskin. Okay, so Månskin numbers count, I think they're called Månskin paths. So in a dyke path, you have an up step, you have a down step, and you're just going to also have a neutral step in a Månskin path. Okay? So you don't have to go up or down every step, you can kind of just go straight if you feel like it. Okay, so how many Månskin paths of length 1 are there? Okay, now importantly, for dyke paths, they were of length 2n, right? And Cn counts the number of length 2n paths. Månskin paths, you can just go straight. Okay, so you actually count paths of length n, because odd numbers are now possible. Right? Okay, cool. So M1, 1. You just have to take one of those. M2, 2. Right, so you can go straight, or you can go up, down. And like dyke paths, Månskin paths can't go below the x-axis. Everyone clear on this? Okay. M3,
3.
Ooh, we have a discussion. Who says 3? You say 3. Which 3?
Straight.
Yeah, so we can go straight.
Up, down, straight.
We can go up, down, straight. Well, let's call it up, down, straight.
Straight up, down. And
Straight, up, down.
And up, straight, down. So it's 4.
Yeah, that's what I was.
Yeah, he conceded.
About to say.
He conceded. You are victorious. Congratulations.
Yeah.
Okay, so right now we've noticed that these are finally something which is not Catalan numbers.
Yeah.
Yeah. Okay, so Månskin numbers then proceed 9, 21, 51. Surprisingly 127, which is 2 to the n minus 1. You'd think there'd be something useful there. Nope. Okay, and here's a general recursive formula for them. N minus 1. Okay, how do we prove this? Anyone? Okay, well, we're going to try break them up again. This looks a lot like I go straight and then do something else. Right? And these also look like, and these look, well, first time that maybe you go up and you hit the ground. You go up, you do a Månskin. Start length I, you go down. And you've used I plus 2, so Månskin I and Månskin n minus 2 minus I. Okay? That makes sense? Okay, good?
Yeah.
Okay, cool. And now, For Motzkin numbers, it turns out that you get, that's easy. Wait, I'll just write it. You also have MN, works out to it's 2, minus 1, minus 3. Okay, now, unfortunately for us, remember that generating function stuff we did for occurrences? And you can get up generating functions and all that good stuff? Yeah. So these aren't constants, so this recurrence isn't linear, so you can't get those. And instead you get that the generating function satisfies this equation. Yeah. And then if you want to break it up and find growth rates and things, well, good luck. And that is what I had for Motzkin numbers and counting sequences. So I'm going to move on to a little bit of game theory. Cool. Okay. So the game theory has a whole lot of branches, but for the two-player games I'm going to talk about, there are sort of two types. The first is zero-sum games. Okay, what do zero-sum games mean? Mean basically my loss is your gain and they are entirely competitive. Right? Okay, so for example, maybe player A has got two options, and so does player B. Okay? He can do heads or tails. And this guy can do head, well, what do you want to call his strategy? He has red and blue as options, ignoring them running a blue egg. Okay, and maybe here, A wins 2. Here he wins 2, and here he loses 2 and B gains 2. Okay, so that's the zero-sum game. I only have to write one number because once I know how much player A wins from player B, I know how much player B loses to player A. They're the exact same number.
So is a positive number A's gain?
Yeah, so a positive number is A wins, a negative number is B wins.
So this is a heads and tails, and this one's just got a 50-50 red-blue.
Well, not exactly. So both players get to, so player A gets to pick, does he want to go heads, tails?
Yeah.
And player B goes, does he want to play red or blue? And the payoff is given by the structure. If I say heads and you say red, I win. But if I say tails and you say red, you win. Okay?
And those are sort of concealed. I mean,
Yeah.
it's not like one person says and then the other person.
No. They make the move at the same time. So here's a classic example, which we've all played. Rock, paper, scissors.
Yeah.
Okay? And the payoff strategy for rock, paper, scissors, the payoff matrix, looks like this. Heads, rock, paper, scissors, rock, paper, scissors. Okay, well, a tie is no one wins, no one loses. If I go rock and you go paper, -1, 1. Paper covers
Rock.
rock. -1. Rock smashes scissors. -1. So?
Wait.
They get. Which one should flip? The last two should flip. Yeah, they should. Thanks. Okay. Now, what is the optimal strategy for rock, paper, scissors?
Read your opponent's mind.
Yeah, reading your opponent's mind works really well, and in practice, people fall into patterns, and
There's no hierarchy.
there's no hierarchy. Yeah, well, so in practice, people do fall into patterns, and you really can win by just go. They'll do the thing that beats what you just did. You do the thing that beats that, which is the thing that loses, and then in practice, that works really well. But really, none of these things are any better than each other. Well, one thing you can.
If you roll a dice and then use that to determine your answer, you would actually play better than if you actually try to choose them.
Well, okay, so there's a few assumptions we've just built in here. Okay, so one thing is, if you actually play rock, paper, scissors, you probably play a lot of repeated games. Okay, this is a once-off. Right? Okay, so in a once-off game, maybe rock is going to work out for you if you know something about like the history or something. Turns out that you want to randomize, and that's an option we'll probably talk about the next lesson. Right? Sometimes just if it depends on what the other guy does, and there's all this interconnection. And no matter what your strategy is, if he's picking at random, you get a 0 payoff. Sometimes you might say, well, I want a 50% chance of winning and a 50% chance of losing over a third of a chance of winning, a third of a chance of losing, and a third of a chance of getting nothing. So exactly what's best just isn't that well specified. And I'll talk those. I'll talk probably next lesson about what exactly best strategy means. Okay, but then we have games which are sometimes called cooperative games, which are not pure, where my loss isn't necessarily your game. See?
What is the name for it?
Sorry?
What is the name for the
So
other game?
these are called zero-sum games,
And the other one?
cooperative games. Cooperative.
Cooperative.
Yeah. So yeah, there's a major card that it's called truce, and because not all victories require a defeat. So that's how it works here. Who's heard of the prisoner's dilemma? Okay, a few of you. So what happens? We drag two people up to be, there's been some crime. We don't know who's done it. We have two prisoners separate, and we say to the first guy, did you do it? And we say to the second guy, did you do it? Okay? And now, their options are to, confess or not confess, right? And you'll see different versions of this. Now, prisoner A can confess or not confess. B can confess or not confess, right? And I'm going to write, and now I'm going to need two numbers for their payoffs. Okay? So, if A confesses and B doesn't, A will spend 10 years in jail, payoff of -10. B will walk free. Right? Similarly, if B confesses and A doesn't, well, guess it's B. A goes free, B will spend 10 years in jail. Okay, what what if they both confess? Sorry? Say?
Then you don't. One of them's lying, so you don't know.
Yeah, but you have to do the same to both of them. Right? So,
Split the sentence.
yeah, let's do that. So, they both go for 5 years. And if they both confess, we will be a little bit more merciful and they'll both get 2 years. Okay? So now, Nash, and yes, the same Nash from that really, really long, badly done movie. He had a really good idea about this, okay, for his PhD thesis. Let's talk about Nash equilibrium. And a Nash equilibrium is a point where no matter what you do, no matter what if you're in one of these points, you can't move it. So therefore you're at equilibrium. Okay? So now it turns out, if you guys could read each other's minds, if you could cooperate, you'd really like to be here. Right? I mean, okay, really you'd like to be here and have this other guy go to jail, but you can't force that. Okay, but if we're both confessing, it's really in my interest to not to. So this is not Nash equilibrium because someone can defect. Okay? This, however, is a Nash equilibrium because if I decide to not confess, so both of them didn't confess. I think I got these the wrong way around. Yeah. Sorry. Should have gone through this. Okay. So yeah, here I'm just going to jump ship. Oh. No. Sorry. So. No. This was right. I'm sorry. Okay, so both people confessed, right? You're at -5 apiece. What am I doing wrong here? Sorry? Sorry?
It wouldn't make sense because you can just not confess then.
So yeah, a confessor cannot confess. But if it's like this, they're both refusing to confess. Okay, sorry, yeah. So if neither of us has confessed.
No.
No?
So, the one who confesses gets screwed, right? We got that.
Well, so the one who doesn't, typically the one who doesn't confess goes free. Yeah?
So, like if one of them confesses and the other one doesn't, the one who didn't confess gets the 10 years.
So? Yeah, the one to confess, he gets 10 years.
The one that does confess.
Now, if you've both confessed,
If you both confess, then you get 5 years in this case.
we've got
Is this the version where you betray the person or you confess yourself?
Yeah, so the point is that if you betray the other guy, he's in trouble. Okay, but it's good for you. But then, so you should both agree. Okay, whatever happens, we're not going to rat each other out. And if you don't, it's better than if you both decide to. But no matter where you are,
So
you can't always want to deny.
Whether you're guilty or not, in fact, it doesn't come into this at all.
No. It's got nothing to do with it.
Yeah.
In this game,
Yeah.
whether you're guilty, if we're playing some morality game, sure. Here in this game, no, you're just trying to get out of it for yourself. Okay, I'm going to start here next time and with accurate numbers. Sorry, this is not been a good class. So there was a TV show I saw once where two guys get to the prize giving. There's a cash prize they've won together, and they have a choice to split or steal. If they both split, they split the money, they go home. And typically it's quite a lot of money, like £10,000 kind of thing. Okay? If they both try to steal it, okay guys, sorry you don't get it. But if one steals and the other one splits, the stealer gets all of it. Okay? So now you're sitting here with this other person who you've just gone through this thing with, and you've got, your whole goal is to convince them that yes, you are going to split. Okay, so what is the correct strategy here? It's not always steal. So, because remember, this isn't exactly Plato's dilemma, because whether you split or steal, if the other guy steals, you're dead. Your goal is to make sure this other guy splits. So my personal favorite version of this is the guy walks up and says, look, I promise you and I give you my word, I am going to steal. So if you don't split, we'll go home with nothing, and I'll split the money with you afterwards. Okay. There's a game of chicken. Okay, you two gets drive cars at each other, and whoever swerves off first loses. Okay, it turns out your best strategy here is to make it clear that the other guy sees you throwing your steering wheel out of the window. So he knows you're not doing it, even if you decide. Okay, so typically in these games we assume there's not this sort of communication ability. And with that, I'll hand you over to Liam, who is... What are you talking about? Are you teaching now?
Oh yeah, doing real numbers.
Real numbers.
Fascinating.
Is that? Sorry?
Real numbers. That's a broad topic.
Yeah. And also there are quite a few of those, so it might take a while.
Yeah.
But I think, for real numbers, like just the rationals, you can take half the first one and half of the second one and so on, but I'm not sure how you do this one. Good luck.